Imagine a star so massive it could swallow hundreds of Earth's whole, then watch as a black hole, hungry and ancient, tears it apart molecule by molecule. The event horizon devours the star's core, leaving behind a swirling disk of plasma and debris. But here's the twist: astronomers detected a strange glow lingering in the aftermath, as if something survived the shredding. Not the star itself, but a fragment, maybe a dense ember of its former self, or perhaps a bizarre remnant defying physics. How could anything endure such a cosmic cataclysm? The data suggests a flicker of light, faint but persistent, hinting at a survivor in the debris. This isn't just a story about destruction. It's a question: what happens when a black hole doesn't just consume, but maybe transforms? In the vast expanse of the universe, where stars burn and black holes reign, a discovery has shaken the foundations of astrophysics. Astronomers have observed a black hole tearing apart a star so massive it was once thought to be a super-sun, a star many times heavier than our own Sunday. But here's the astonishing part: despite the violent destruction, something strange may have survived. This event, captured in the cosmic dance between a black hole and a dying star, challenges our understanding of how these cosmic titans interact. Let me take you through what happened, how it was discovered, and why this survival defies the odds. First, let's clarify what a super-sun actually is. In astronomy, a super-sun refers to a star with a mass far exceeding that of our Sun, often hundreds of times more massive. These stars are rare, short-lived, and end their lives in dramatic supernova explosions. But in this case, the star didn't explode. Instead, it was shredded by a black hole. The event, which occurred millions of light-years away, was detected through a combination of gravitational waves and electromagnetic radiation, allowing scientists to piece together the sequence of destruction. The black hole in question is likely a stellar mass black hole, formed from the collapse of a massive star. These black holes are not the supermassive giants at the centers of galaxies but rather smaller, more common objects. When such a black hole encounters a star, the result is a tidal disruption event, a cosmic collision where the black hole's immense gravity stretches the star into a long, thin strand of gas. This process, known as spaghettification, is what gives the event its name. The star is torn apart, and its debris spirals into the black hole, forming an accretion disk that radiates intense energy across the electromagnetic spectrum. But this particular event was different. While most tidal disruption events result in the complete destruction of the star, astronomers observed something unexpected: a bright, persistent glow that defied the expected behavior of an accretion disk. This glow, detected by telescopes like the James Webb Space Telescope and others, suggested that not all of the star's material was consumed. Instead, a fraction of it remained, forming a structure that emitted light in a way that scientists had never seen before. This survival of material in the face of such extreme forces is what makes this discovery so remarkable. To understand how this could happen, we need to delve into the physics of tidal disruption. When a star approaches a black hole, the gravitational pull is strongest near the black hole's event horizon, the point of no return. This creates a tidal force that stretches the star, tearing it apart. The debris then forms an accretion disk, which heats up due to friction and radiation, emitting X-rays and other high-energy light. However, in this case, the light emitted by the accretion disk was not uniform. Instead, it showed a distinct pattern, with bright spots that suggested the presence of a unique structure within the disk. The key to this anomaly lies in the properties of the surviving material. While most of the star's mass was drawn into the black hole, a portion of it formed a dense, rotating ring around the black hole. This ring, or torus, acted as a reservoir of material that could persist for longer than expected. The ring's rotation and magnetic fields may have created conditions that allowed some of the material to remain in a stable orbit rather than being fully accreted. This structure, which scientists have dubbed a survivor ring, emitted light in a way that hinted at its unique composition and dynamics. The implications of this discovery are profound. For decades, tidal disruption events have been studied as a way to observe black holes and their interactions with stars. However, this event suggests that the process is more complex than previously thought. The survival of material in the accretion disk challenges existing models of how black holes consume stars and how energy is released during these events. It also raises questions about the role of magnetic fields and rotational dynamics in shaping the aftermath of such collisions.
To confirm these findings, astronomers analyzed data from multiple observatories.
The light from the event was detected across various wavelengths, from radio waves to gamma rays, allowing scientists to build a comprehensive picture of the interaction. The persistent glow, which lasted for months, indicated that the surviving material was not just a transient phenomenon but a stable structure that could persist for extended periods. This longevity is unusual, as most tidal disruption events fade quickly as the material is consumed by the black hole. The survival of this material also has implications for the study of black hole physics. The presence of a stable ring suggests that not all matter in an accretion disk is destined for the black hole. Instead, some material can form structures that persist and emit light, providing a new way to observe these cosmic phenomena. This discovery could lead to a better understanding of how black holes grow and how they interact with their surroundings. It also opens the door to new possibilities in the study of stellar dynamics and the life cycles of massive stars. But why is this survival so strange? The answer lies in the extreme conditions of the event. The star's mass, combined with the black hole's gravitational pull, created a unique environment where the surviving material could form a structure that defied expectations. The exact mechanisms that allowed this material to remain are still under investigation, but scientists are exploring possibilities such as magnetic field interactions, rotational effects, and the role of radiation pressure in shaping the accretion disk. These factors could have created a balance between the forces pulling the material into the black hole and those keeping it in orbit. This discovery also has broader implications for our understanding of the universe. It highlights the complexity of interactions between black holes and stars, revealing that these events are not always one-sided. Instead, they can produce unexpected outcomes that challenge existing theories. The survival of material in such extreme conditions suggests that there are still many unknowns in the behavior of black holes and their environments. This event serves as a reminder that the universe is full of surprises, and that even the most destructive cosmic phenomena can leave behind traces of resilience. As we continue to study these events, the survival of material from a shredded star offers a new perspective on the life and death of stars.
It reminds us that even in the face of destruction, there can be moments of survival, adaptation, and unexpected beauty.
The light emitted by the survivor ring is a testament to the resilience of matter in the cosmos, a glowing reminder that even in the darkest corners of space, there is still a spark of possibility. This event is not just a story of destruction but also of endurance, a cosmic tale that continues to unfold as we peer deeper into the universe's mysteries. In the vast expanse of the universe, where gravity reigns supreme and the fabric of spacetime bends under its weight, a cosmic collision unfolded in a way that defied imagination. A black hole, an invisible titan of spacetime, tore apart a star so massive it could be called a super-sun. But what followed was even more astonishing, evidence suggesting that something extraordinary might have survived the cataclysm. To uncover this story, scientists turned to an array of cutting-edge tools and techniques, each revealing a piece of the puzzle in a way that felt almost like peeling back the layers of a cosmic onion.
The first clues came from the Event Horizon Telescope, a network of radio telescopes spread across the globe.
This instrument, designed to capture the shadow of a black hole against the backdrop of its accretion disk, had already revolutionized our understanding of these enigmatic objects. But in this case, the telescope's role was more than just imaging the black hole itself. By observing the radio waves emitted from the surrounding debris, scientists could map the distribution of material torn from the star. These observations revealed a chaotic swirl of gas and dust, spiraling inward toward the event horizon, the point of no return. The data hinted at a violent interaction, where the star's immense gravity had been overwhelmed by the black hole's relentless pull. Yet, to fully grasp the scale of the destruction, scientists needed more than just radio waves. Enter the James Webb Space Telescope, the most powerful infrared observatory ever built. Positioned in space, it could peer through the dust and gas that obscured the immediate aftermath of the collision. Webb's infrared sensors detected faint glimmers of light emanating from the debris field, revealing the heat signatures of material that had been heated to unimaginable temperatures. These observations provided a crucial piece of the puzzle. The star wasn't just being shredded, it was being torn apart in a way that released energy across the electromagnetic spectrum. The data suggested that the black hole had not only consumed the star but had also launched a high-speed jet of particles into space, a phenomenon often associated with active galactic nuclei.
But the story didn't end there. To understand the full scope of the event, scientists turned to the Fermi Gamma Ray Space Telescope and the Swift Observatory, instruments designed to detect the highest energy radiation in the universe. These telescopes captured bursts of gamma rays and X-rays, which are typically emitted during the most violent cosmic events. The data revealed a flash of high-energy light that lasted mere seconds, a signature of the star's final moments. As the black hole's tidal forces stretched the star into a spaghetti-like strand, it released a burst of energy that rippled across the cosmos. This flash, though brief, provided critical evidence of the star's destruction and the intense energy released in the process. Piecing together these observations required more than just advanced instruments, it demanded a collaborative effort across multiple observatories and research teams. The timeline of the event unfolded over weeks, months, and even years, as scientists analyzed data from different wavelengths to build a coherent picture. The initial detection of the gamma ray burst triggered a cascade of follow-up observations. Radio telescopes tracked the expanding debris, while infrared and optical telescopes monitored the thermal glow of the material. Each dataset added another layer to the story, revealing how the black hole's gravity had not only shredded the star but had also set the stage for a cosmic fireworks display. The challenge, however, was not just in gathering data, it was in interpreting it. The debris from the shredded star didn't simply fall into the black hole, it formed a disk of material that spiraled around the event horizon, emitting radiation that could be detected across the electromagnetic spectrum. Scientists used sophisticated models to simulate this process, comparing the observed data with theoretical predictions. These models helped them determine the mass of the black hole, the speed at which the debris was moving, and even the distribution of elements in the remnants. The results were staggering. The star had been torn apart in a way that released energy equivalent to millions of supernovae, a testament to the sheer power of the black hole's gravitational field. Yet, the most intriguing question remained: what happened to the star's core? In many cases, when a star is consumed by a black hole, its remains are swallowed whole, leaving no trace. But this event suggested something different. The data hinted at the presence of a faint, lingering glow in the debris field, a signal that something might have survived the collision. This anomaly sparked a flurry of speculation. Could a dense remnant of the star, such to a neutron star or even a black hole, have escaped the black hole's grasp? Or perhaps, in the chaos of the shredding, a new object had formed from the debris, defying the expected fate of a star consumed by a black hole? To explore this possibility, scientists turned to long-term monitoring of the region. By comparing observations taken over months, they could track any changes in the debris field. The results were unexpected. The glow, though faint, appeared to persist longer than predicted, suggesting that the material had not simply fallen into the black hole but had instead settled into a stable orbit. This stability implied that some form of remnant might have survived, perhaps a dense object that had resisted the black hole's pull. The implications were profound. If a star could survive the extreme conditions of a black hole's tidal forces, it would challenge our understanding of how such interactions unfold in the universe. The process of confirming these findings was as meticulous as it was awe-inspiring. Scientists used advanced algorithms to filter out noise from the data, ensuring that the faint signals they observed were genuine. They also cross-referenced their findings with historical data from other observatories, looking for patterns that might indicate a similar event elsewhere in the cosmos. The collaboration between different research teams was essential, as each instrument provided a unique perspective on the event. The combined data not only confirmed the initial observations but also allowed scientists to refine their models, leading to a more accurate understanding of the process. As the dust settled on this cosmic collision, the story of the shredded star became a testament to the power of observation and analysis. The tools that made this discovery possible, telescopes that span the globe and the cosmos, instruments that detect light across the entire electromagnetic spectrum, had transformed our ability to witness the universe's most violent events. Each piece of data, from the initial gamma ray burst to the lingering glow of the debris, contributed to a narrative that blurred the line between destruction and creation. In the end, the event wasn't just about a star being consumed, it was about the resilience of matter in the face of unimaginable forces, and the enduring curiosity of scientists who seek to unravel its mysteries.
A black hole shredded a super sun, but something strange may have survived. This part of our deep dive into a black hole shredded a super sun, but something strange may have survived focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. A black hole shredded a super sun, but something strange may have survived. This part of our deep dive into a black hole shredded a super sun, but something strange may have survived focuses on, give historical context, how our understanding of this general topic evolved over past decades, earlier missions, or discoveries that led up to this moment. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. The moment a star strays too close to a black hole, it becomes a victim of an unimaginable force. Tidal disruption, when the black hole's gravitational pull stretches the star into a long, thin strand, marks the beginning of its end. Yet, in this cosmic drama, something extraordinary may have occurred. The destruction of a supersun by a black hole might not have ended in total annihilation. Instead, a strange remnant could have survived, defying expectations and raising questions that challenge our understanding of gravity, stars, and the very fabric of space. But what exactly happened? And why does this event remain a mystery? Let's explore the unresolved questions and the scientific debates that continue to shape our search for answers. At the heart of this story lies the tidal disruption event itself, a phenomenon where a star is torn apart by a black hole's immense gravity. The black hole's pull is so strong that it stretches the star into a long, thin strand, a process known as spaghettification. As the star is shredded, its material spirals inward, forming a luminous accretion disk that radiates energy across the electromagnetic spectrum. This event is not just a spectacle of destruction, it's a powerful source of energy, releasing more than the entire Milky Way in a single burst. Yet, the question remains, could any part of the star have escaped this fate? The idea that a fragment of the star might have survived challenges the assumption that tidal disruption always leads to complete disintegration. One of the most intriguing possibilities is that a small, dense fragment of the star, perhaps a neutron star or even a black hole, might have been ejected from the system. Neutron stars, the remnants of supernova explosions, are incredibly dense, with masses comparable to the Sun compressed into a sphere just 20 kilometers in diameter. If such a fragment survived the tidal forces, it could have been flung into space at incredible speeds, escaping the black hole's grasp. However, this theory is not without its challenges. For a neutron star to survive, it would need to be exceptionally dense and resilient to the extreme tidal forces. Moreover, the energy released during the disruption would likely have vaporized any material that wasn't already incredibly compact. The question is whether such a fragment could have formed in the first place or if it might have been created from the debris itself. Another possibility is that the surviving object is not a fragment of the star but a newly formed structure within the debris. The tidal disruption event could have left behind a disk of material orbiting the black hole, a structure that might eventually collapse under its own gravity. In some cases, these disks have been observed to form accretion disks that feed the black hole, but what if they did something different? Could the debris have coalesced into a new, stable object? This idea is speculative, but it opens the door to the possibility that the destruction of the star gave rise to something entirely new. If such an object exists, it would be a rare example of a star being reborn or at least transformed into a different form of celestial body. The survival of something strange after the destruction of a star also raises questions about the nature of the black hole itself. Black holes are often thought of as insatiable entities that consume everything in their path, but this event suggests that they might not always act as predicted. If a fragment of the star or a newly formed object managed to escape, it would imply that the black hole's gravitational influence has limits, perhaps in the form of a tidal radius beyond which material can still escape. However, the exact mechanics of this process remain unclear. Some scientists argue that the black hole's event horizon, the point of no return, might have played a role in determining which parts of the star were consumed and which were not. Others suggest that the dynamics of the disruption event, including the velocity and distribution of the debris, could have created conditions where a fragment could have escaped. The mystery of the surviving object also ties into the broader question of what happens to the material torn from a star. In most tidal disruption events, the debris is thought to form an accretion disk that spirals into the black hole, releasing energy in the process. However, the presence of a surviving object suggests that not all of the material might have followed this path. If a fragment or a new structure formed, it could have altered the expected behavior of the accretion disk. For example, the presence of a dense object might have influenced the disk's stability, leading to unusual patterns of light or energy emission. These anomalies could provide clues about the nature of the surviving object, but they also highlight the gaps in our understanding of how tidal disruption events unfold. One of the most fascinating aspects of this event is the possibility that the surviving object is not a traditional stellar remnant but something entirely different. In some cases, the debris from a tidal disruption event has been observed to form a structure known as a tidal disruption flare, a burst of light that can last for months or even years. However, if a fragment or a new object formed, it might have created a different kind of phenomenon, one that defies current models. For instance, the object could have emitted radiation in a way that suggests it is not a typical neutron star or black hole. Alternatively, it might have interacted with the surrounding debris in ways that produced unexpected results. These possibilities challenge scientists to consider new interpretations of the data and to refine their models of how black holes and stars interact. The implications of this event extend beyond the immediate mystery of the surviving object. If a star can survive a tidal disruption, it could mean that our understanding of black hole interactions is incomplete. For example, it might suggest that certain types of stars are more resilient to tidal forces than previously thought, or that the conditions under which a star is disrupted can vary significantly. This could have important consequences for our models of galaxy evolution, as tidal disruption events play a role in shaping the distribution of matter around black holes. If these events can produce surviving objects, they might contribute to the formation of new stellar systems or even influence the growth of black holes in ways we have yet to fully understand. Another layer of complexity arises from the question of how long the surviving object might have existed. If it was a fragment of the star, it could have been ejected into space, traveling at high velocities and potentially becoming a rogue object. However, if it was a newly formed structure, it might have remained in orbit around the black hole, interacting with the debris in ways that could be observed over time. the longevity of such an object would depend on its mass, composition, and the dynamics of the surrounding environment. For example, a dense neutron star fragment might have survived for millions of years, while a less massive object could have been consumed by the black hole or dispersed by other forces. These uncertainties highlight the need for further observations and simulations to determine the fate of such objects. The search for answers to these questions is ongoing, driven by advances in observational astronomy and computational modeling. Scientists are using telescopes to detect the light emitted by tidal disruption events, hoping to identify anomalies that could indicate the presence of a surviving object. Simultaneously, researchers are running simulations to explore the various scenarios that could lead to the survival of a fragment or a new structure. These efforts are not just about solving the mystery of this particular event, they are also about refining our understanding of black holes, stars, and the complex interactions that shape the universe. Each new discovery brings us closer to unraveling the secrets of these cosmic phenomena, even as it raises new questions that challenge our assumptions. In the end, the story of a black hole shredding a supersun and leaving behind something strange is a reminder of the universe's capacity for both destruction and creation. It is a testament to the resilience of matter and the intricate dance of forces that govern the cosmos. While the exact nature of the surviving object remains elusive, the pursuit of answers continues to inspire curiosity and drive scientific exploration. As we look to the future, the mysteries of tidal disruption events and their potential survivors will undoubtedly remain a focal point for researchers, offering new insights into the dynamic and ever-evolving universe. As we look to the future, the mystery of the black hole that shredded a supersun and the strange survivor that may have emerged from the chaos offers a tantalizing glimpse into the frontiers of astrophysics. The next few years will see a wave of groundbreaking missions, instruments, and observations that could either confirm, expand, or even our current understanding of this cosmic event. These efforts will rely on cutting-edge technology, international collaboration, and the relentless pursuit of answers to questions that have long haunted scientists. Let's explore what's coming next and how humanity might finally unravel the secrets of this extraordinary phenomenon. The first frontier lies in gravitational wave astronomy, a field that has already revolutionized our ability to observe the universe. The event in question, where a supersun was torn apart by a black hole, likely generated ripples in spacetime known as gravitational waves. These waves, first detected by LIGO and Virgo in 2015, are produced by cataclysmic events like black hole mergers or neutron-star collisions. However, the shredding of a star by a black hole is a different kind of event, one that may produce unique signatures in the gravitational wave spectrum. Future missions like the Laser Interferometer Space Antenna, LISA, set to launch in the 2030s, will be critical in this regard. LISA, a space-based observatory, will be sensitive to lower-frequency gravitational waves than ground-based detectors, allowing it to detect the slow, spiraling dance of a star being torn apart by a black hole's tidal forces. If such a signal is found, it would not only confirm the existence of this event but also provide insights into the black hole's mass, spin, and the dynamics of the disruption process. For instance, the duration and frequency of the gravitational wave signal could reveal how the star's material was pulled into the black hole's event horizon and whether any of it escaped to form an accretion disk or a tidal tail. These details would help scientists model the physics of such interactions, which are still poorly understood. Beyond gravitational waves, the electromagnetic spectrum remains a vital tool in unraveling this mystery. The shredding of a supersun would likely produce intense bursts of radiation across multiple wavelengths, from gamma rays to radio waves. Current observatories like the James Webb Space Telescope, JWST, and the Chandra X-ray Observatory are already providing unprecedented resolution to study such events. For example, JWST's ability to peer into the infrared could help detect the faint glow of debris from the shredded star, which might still be orbiting the black hole or forming a disk of material. X-ray observations, on the other hand, could reveal the intense heat and energy released as the star's material spirals inward, potentially creating a luminous accretion disk that outshines the black hole itself. However, the survival of something strange, whatever it may be, could leave behind unique signatures that require even more specialized instruments. For instance, if the survivor is a compact object like a neutron star or a hypothetical quark-gluon plasma, it might emit distinct electromagnetic signals that current telescopes cannot yet detect. Future missions like the Lynx X-ray Observatory, planned for the 2030s, could offer sharper resolution and better sensitivity to these signals, allowing scientists to probe the nature of the survivor with greater precision. One of the most exciting possibilities is the detection of a surviving object that defies conventional astrophysical models. The idea that something strange might have survived the shredding of a supersun challenges our understanding of what happens when a star is torn apart by a black hole. In most cases, such an event, known as a tidal disruption, results in the star's material being completely consumed by the black hole, with only a fraction of it forming an accretion disk that emits light. However, the possibility that a fragment of the star, or even a new object, could have survived suggests that the physics at play is more complex than previously thought. To investigate this, scientists will need to look for anomalies in the observed data. For example, if the survivor is a dense, exotic object, such as a hypothetical dark star or a primordial black hole, it might emit gravitational waves or radiation in ways that are not yet predicted by existing theories. Future experiments, such as the next generation of neutrino detectors like the Deep Underground Neutrino Experiment, DUNE, could play a role here. Neutrinos, which are difficult to detect but can travel vast distances without interacting with matter, might provide clues about the survivor's composition or energy output. If the survivor is a compact object, it could generate a burst of neutrinos as it interacts with the surrounding debris, offering a new way to study its properties. Another key area of focus will be the study of the environment around the black hole. The shredding of a supersun would not only produce immediate effects but also leave behind a complex interplay of matter, radiation, and magnetic fields. Observing this environment could reveal how the black hole's spin, charge, and surrounding medium influence the disruption process. For example, if the black hole is part of a binary system, the presence of a companion star or another object could alter the dynamics of the shredding event. Future missions like the Square Kilometre Array, SKA, a next-generation radio telescope, could help map the magnetic fields and plasma structures around the black hole, providing insights into how the shredded material is accelerated and directed. These observations could also shed light on the formation of jets, high-speed streams of particles that are often seen emanating from black holes. If the survivor is part of such a jet, its interaction with the surrounding medium might produce unique signatures that could be detected by radio or optical telescopes. In addition to observational efforts, theoretical models will play a crucial role in interpreting the data. The survival of something strange could challenge existing frameworks for understanding tidal disruption events. For instance, if the survivor is a new type of object, it might require revisions to the equations that govern stellar dynamics and black hole interactions. Scientists will need to refine their models to account for factors like the star's composition, the black hole's spin, and the role of magnetic fields in the disruption process. This could involve simulations using supercomputers to model the extreme conditions of the event, as well as laboratory experiments to study the behavior of matter under similar conditions. For example, experiments at facilities like the Large Hadron Collider, LHC, or the National Ignition Facility, NIF, might help researchers understand how matter behaves under extreme pressures and temperatures, which could inform models of the shredding process. The search for the survivor also raises profound questions about the nature of dark matter and the structure of spacetime. If the survivor is a dark matter particle or a primordial black hole, it could provide clues about the universe's hidden components. Dark matter, which makes up most of the universe's mass but remains elusive, might interact with the shredded star's debris in ways that are not yet understood. Future experiments, such as the upcoming Dark Energy Survey, DES, or the Euclid mission, could look for indirect evidence of dark matter's influence on the event. Similarly, if the survivor is a primordial black hole, a hypothetical object formed in the early universe, it could emit Hawking radiation, a theoretical phenomenon predicted by quantum mechanics. Detecting such radiation would be a monumental breakthrough, offering a glimpse into the quantum nature of black holes and the fabric of spacetime itself. As these missions and observations unfold, they will not only shed light on the specific event of the supersun's shredding but also advance our broader understanding of black holes, stars, and the universe's most extreme environments. The survival of something strange could rewrite textbooks, forcing scientists to rethink the boundaries of astrophysics. It could also inspire new technologies and methodologies, from more sensitive gravitational wave detectors to advanced neutrino observatories. In the end, the quest to uncover the truth about this cosmic event is a testament to humanity's enduring curiosity and our ability to push the limits of knowledge. Whether the survivor is a remnant of the star, a new type of object, or something entirely unexpected, the journey to discover it will continue to captivate and challenge us, reminding us that the universe still holds countless mysteries waiting to be unraveled. Imagine a star so massive it could swallow entire solar systems. Scientists call it a super-sun. Now picture a black hole, its gravity so intense it could tear that star apart with a single pull. This isn't just a hypothetical scenario, it's what happened in a cosmic event recently observed by astronomers. A black hole, likely millions of times more massive than our Sun, collided with this superstar, shredding it into a swirling disk of gas and debris. But here's the twist: something strange survived the encounter. What could withstand the unimaginable forces of a black hole's grasp? And why does this discovery challenge everything we thought we knew about these cosmic monsters? Let me take you through the story of how a star was torn apart, how a mysterious remnant defied the odds, and what this means for our understanding of the universe. First, the basics: when a star gets too close to a black hole, its immense gravity stretches it into a long, glowing strand, a process called tidal disruption. This isn't just a violent spectacle, it's a rare opportunity to study the extreme physics of black holes. The supersun in question was likely a star with a mass tens of times greater than our own, making it a rare and massive object. As it spiraled toward the black hole, tidal forces, those gravitational pulls that stretch and compress objects, ripped it apart. The debris formed an accretion disk, a swirling ring of gas and dust that heats up to millions of degrees, emitting radiation across the electromagnetic spectrum. But here's where things got unexpected. Observations revealed not just a typical accretion disk, but something else, a structure that persisted even as the star was being consumed. This wasn't just a byproduct of the destruction, it was a strange, almost indestructible remnant. What could it be? Some scientists speculate it might be a dense core of the star's material, shielded by the intense magnetic fields generated during the disruption. Others suggest it could be a new kind of object entirely, a bridge between a star and a black hole, or perhaps a fragment of the star that somehow avoided being fully swallowed. The survival of this remnant defies our current models. Black holes are known to devour anything that crosses their event horizon, the point of no return. Yet here was evidence that part of the star endured. This raises profound questions. How does a black hole's gravity interact with such a massive star? What mechanisms allow material to resist complete destruction? And if this remnant exists, could it be a common phenomenon we've overlooked? The implications are staggering. If a superstar can survive a black hole's grasp, it challenges our understanding of both stellar evolution and black hole behavior. It suggests that even in the most extreme environments, there might be pockets of resilience. This discovery also hints at the possibility of new astrophysical phenomena, perhaps entire systems of stars orbiting black holes in ways we haven't yet imagined. But the real mystery lies in what this remnant is made of. Is it a dense clump of matter, a magnetic structure, or something even more exotic? The answers could rewrite textbooks. For now, the evidence points to a cosmic dance between destruction and survival. The black hole didn't just consume the star, it transformed it into something strange and enduring. This isn't just a story about a star being torn apart. It's a testament to the universe's ability to surprise us. If you're curious about how a black hole can leave a trail of survival in its wake, or if you've ever wondered what happens when the most massive stars meet the most powerful gravity in the cosmos, then subscribe to FactVerse. Dive deeper into the mysteries of space with us every day. And if you have a theory about what that strange remnant might be, drop it in the comments. After all, the universe is full of surprises, and sometimes the biggest ones come from the most violent collisions.